All right, guys. So today we are talking about something that's really important topic in calculus. We're talking basically about how to use the first and second derivative to figure out characteristics of the original function f of x. So this is still falling in the realm of, if you were in AP pre-calc last year, you saw this. So just remember, like, it's a good opportunity to master it. And if you were in regular, sorry, this is brand new, but I'm going to teach it as though you've never seen it before, as though everyone's never seen it before. So what I did was on Desmos, I graphed a function, just a random like cubic function that looked nice. And then I had Desmos graph the derivative so that this picture right there, that is the literal f prime of x based on the function. And then on the back, we have the original function and the second derivative. And I would recommend save this paper and keep it separate from the rest of your notes so that you can reference it quickly, because the concepts that we're going to talk about today, we're going to see a lot throughout the year. And until you have them memorized or really know them, you're going to want to have this in easy access. So anyways, what I'm going to do here, I'm going to use some different colors as well. So you guys could do that, and you can use like pencil and pen, or if you have different color pens, etc. It'll be helpful. And so what we're going to look at first is where this graph f of x is increasing. So I'm going to highlight that in red, which I know is a little confusing because my function's already red, but I'll do the decreasing part in blue in a second. It'll stand out. So what we are going to do now is we're going to draw in some tangent lines, just a bunch of little tangent lines here to the curve for those increasing intervals. And what would we say about the slopes of all of these tangent lines? They're all positive. And when I say slope of a tangent line, what's another word that we use to be a synonym for that? The derivative. So what this means is if the slopes of the tangent lines are positive, it means the derivative is positive. Or usually what we'll just say is it's greater than 0. And so we can see that it's increasing basically until -2 and somewhere around like 1/2, or something like that, 4/7, some weird fraction. But if we look down at the derivative, we should notice that f prime of x is positive on those exact same intervals. And so we'll write the reverse here. And we'll write that if f prime of x, the derivative, is greater than 0, then f of x is increasing. So let's do the same thing for where f of x is decreasing. Highlight that in a different color. I'm going to use blue. Draw in some tangent lines. And then we'll talk about our conclusions here. All right, so what would we say about the slopes of the tangent lines when f of x is decreasing? They're negative. Which means f prime of x is negative. Or we could say less than 0. And so we'll do the same thing for the derivative as well. There's the negative part right there below the x-axis. I'll just have it here so we can see them both. Okay, turn and talk to your neighbor. What happens when f prime of x equals 0? Okay, so what happens in the graph of f of x when f prime of x equals 0? Yeah, we have turning points, maximums or minimums. We have horizontal tangent lines, all of those things. So we'll say here if f of x is changing from what to what? What's f of x doing? It's changing from increasing to decreasing or decreasing to increasing, yes. So when f of x changes from increasing to decreasing or vice versa, we have a horizontal tangent line. And that means that the derivative, sorry, not double prime, getting ahead of myself here, just f prime, equals 0. But it doesn't just equal 0. Something specific, or a way to be more specific is, and it changes sign. So it's changing from positive to negative. Because it is possible to have a horizontal tangent line that's not a max or a min. Like it could flatten out and then keep growing. Because it's not changing from increasing to decreasing. Or a derivative would not be changing signs there. But, so just so you know. So let's write that down here. If f prime of x equals 0 and changes sign, if it changes from positive to negative, what type of extrema do we have? So that's like our first 0 right here. What do we have in the original function? We have a maximum, yes. So we can call that a local max or a relative max. Either one is fine. And if the derivative changes from negative to positive, we have a local or a relative minimum. And I'll say this right here, this is we kind of wrote it forwards and backwards, looking at f of x, looking at f prime of x. We are usually going to be looking at the first derivative to talk about the original function. But it's good to know that it does work both ways. So this is the kind of thing that, again, you want to have easy access to these notes until you got it more than just memorized. Like, this is living in your brain and in your heart. You know this backwards and forwards, because we're just going to see it probably every day for the rest of the year. Okay, let's talk about the second derivative. Now, first of all, if I have the first derivative, how would I get the second derivative? Yeah, the slope of the tangent line of the first derivative, or it would be just like the derivative of the derivative, right? So the relationship between f double prime and f prime, the first and second derivative, is the same relationship that exists between f prime and f, right? One's just the derivative of the other. So what we should see, this is not what we're highlighting today, but where f prime of x is increasing, we should see f double prime being positive on those values. And where f prime is decreasing is where the second derivative is negative. So it's the same relationship. Right now we're going to look at the connection between the second derivative and the original function. And what the second derivative tells us about is concavity. So right here, from roughly there and all of this, we would say that f of x is concave up, which basically means it has this kind of upward curved shape. But it can be increasing or decreasing, but it's kind of that curved shape. What concave up means, here's how it's defined, is when you draw tangent lines, they are below the curve. That's just the definition of it, but what we're going to notice is that the second derivative is positive, is greater than 0 on those intervals. So think concave up, f prime of x greater than 0. And then if you draw a picture of it, you'll see where the tangent lines go. Oops. So that's this interval right there. Oh. And we can abbreviate that CCU for concave up. I don't know how I just like forgot how to write for you guys. I was writing fine in first period. CCU. There we go. Question? Oh. And then we're going to see the reverse of this for where f is concave down. So concave down, it has this downward shaped curve. It means that the tangent lines are here above the curve. That's like the actual definition of concave down. And that means our second derivative is going to be less than 0. It's going to be negative. Okay. Now, at this point right there, where f of x changes concavity, do we know what that's called? Point of inflection, yes. And so that's corresponding to the second derivative equaling 0 and what else? Changes sign, yes. And we can abbreviate that POI, person of interest. Okay, so again, save this paper, memorize this. This is the part that we're usually looking at. We're usually examining the second derivative and then making conclusions about f of x. We're going to do an example here with both of these, and you can just put that on a regular piece of paper, but keep this one handy. I'll give everyone a chance to finish writing. Okay. So here's the example we're going to do. And you know, if you have this in your notes and you're labeling and keeping up with everything, this is 2.5. Notes continued. So just to help you organize. So, turn to your neighbor. Which of these things are we able to do with the first derivative, and which of these things are we able to do with the second derivative? Talk about it. Okay. Yes, you guys are getting it right. I did also sort it by which one goes with which. So we're going to do local extrema, intervals of increasing and decreasing first with the first derivative. Okay, so let's take the derivative. And then we really want to know some very specific information about this derivative right away. What do we want to know? Yes, we want to know the x-intercepts. Yes. The zeros, the x-intercepts, the roots, the solutions, etc. So as we're doing that, of course, you know, we got to factor this. So take out that 6. And then factor. And then we can say something like, you know, you can say something like this: f prime of x equals 0 at x equals -2 and -1. You could write 0 there and then just say x equals -2, x equals -1. But basically we need to show that you're setting the first derivative equal to 0. So that's kind of like that's usually worth a point in an FRQ. Some indicator that you're setting the first derivative equal to 0. Then what we have to do is this is throwback to pre-calculus. We've got to make a number line with our zeros, and we have to do a number line test. Make sure you label the number line. Because we really want to know where the first derivative is positive and where it's negative, because that's going to tell us where the function is increasing and decreasing. So remember, for a number line test, any x value in this region, like -3, -4, -5, etc., would tell us positive or negative for that region, and you just plug it into the derivative. Whichever version feels the easiest, I would recommend that one. We do the same thing for something like -1.5, -1.1, whatever feels easy. And then for this region, we can use any number greater than -1, but we should probably use 0. Yeah, it's definitely the easiest number right there. So when we plug in -3, I can see like, oh, that's negative, that's also negative. So this is a positive value. -1.5 would make this positive, but this negative. So remember, we don't really actually care what the real y value is. We just want to know positive or negative. And then if I plug in 0, it's going to equal 12, because that's the y-intercept there. What this is called here is this is called the first derivative test. And it's just referring to a number line test with the first derivative to find the extrema. And we need to show the number line. It needs to be labeled. It has to have the positives and negatives in there. That's the only way to justify this, is by having a number line there. Now, you might notice there's some fast ways to do number line tests, if you remember. This is going to make what kind of shape? Parabola, right? It's a positive parabola. Okay, so we know it's going to come down through those roots like that. So it's going to go positive, negative, positive. So if you want to save a little time and not plug points in, this is how I do it. I hate plugging points in. I make mistakes all the time. We still need to have the number line there. So just, you can picture in your mind positive, negative, positive, just label it, put it there. Do the number line tests quickly. Okay, so turn to your neighbor. What does this mean? What does our first derivative test tell us about increasing, decreasing, maxes, and mins? Okay, we'll fill this out when we come back from lunch. Okay, so we're gonna fill this out with this information. Go ahead and start writing this down and talk about it with your neighbor. Just kind of bring yourself back post lunch. This is how we want to phrase these things, though. Okay, so positive or negative here, where f of x is increasing. Positive parts or negative parts. Which tells us increasing, positive or negative? Positive. Okay. So increasing on negative infinity to negative 2 and negative 1 to infinity. You can use brackets or parentheses there, actually. Brackets is sort of the more correct, but it doesn't actually matter. And that's because f of x is greater than 0. And so then we are decreasing on negative 2 to negative 1 because f of x is less than 0. And again, with increasing and decreasing, you could use parentheses. That's fine. Just don't do something like this where you use a parentheses for one number and a bracket for the other number. That's weird. Don't do that. But either way, it's fine. Where does f of x have a local maximum? Negative 2. Okay, because f prime changes from, and then local minimum at x equals, obviously it's the other one, right? For the other reason. So this is the kind of explanation that we have to do whenever we're answering a question like this. Make sure you specifically name the functions that you're talking about. So I'm not saying anything like, I see this all the time, but f of x is increasing because it is positive. What does that mean? Because f of x is positive? Because the derivative is positive? Because some crazy clown alien that lives in a sewer is positive? That's what I think of when you say it. Okay, I think of that. So don't say it. Always name what you're talking about. F of x is increasing because f prime is greater than 0. So for all those things. Okay. And again, this is called the first derivative test, what we just did. Questions on that? Okay. So go ahead and take the second derivative, and we will look at how to find concavity, points of inflection, and such like. You could take the derivative of any version of f prime of x. I would recommend you just go with the original because it's just power rule. And then we want to say something like this. F double prime of x equals 0 at x equals, what would it be in this case? Yep. So same deal, we're going to do a labeled number line. This is not the second derivative test. There is a thing called the second derivative test, and it's not this. We'll talk about it next class. So it's just a number line test for concavity. Same deal for this. Like if we can picture that function f double prime of x it can make our number line test pretty easy. It's also easy in general because it's an easy function, but that's a line, right? So does it look like this or like this? Positive slope or negative slope? Positive. So that means on the left side here, it's going to be negative and then go positive because our line's going to go like that and pass through the 0. So make your life a little easier. And so turn to your neighbor. What do we know about concavity and points of inflection because of what we see here, and how are we going to write it?
And as it changes signs.
I think this would be
Okay, so where is f of x concave up? Same deal here, you can use brackets or parentheses. And that's because f double prime of x is greater than 0. F of x is concave down. The other part of the graph, or the other part, because f double prime is less than 0. So I guess before we say f of x has a point of inflection, does f prime double prime, oh man, does f of x have a point of inflection? Yes, at x equals, because f double prime of x equals 0 and changes sign, yes. We can just say because it changes sign, because we've already said that it equals 0 up there. But we can also say this. Ew. Okay, so again, we have to write a sentence. It's super rare that we would have to find all of these things about one function. This is basically just the example to show how you would find each of those things. It's normally going to be like an FRQ where it says, here's this function s of t, whatever it is. Where is s of t concave up? And so you just have to do 2 derivatives, a number line test, and have one of these answers, not all of this stuff. So just so you know. There's one more slide here that we're going to have. So this is relevant for the first derivative test. There are these things called critical values or critical points. So this is where f prime of x equals 0 or f prime of x is undefined. So all of our critical values need to go on the number line whenever we're doing our first derivative test. And so what we just were talking about and looking at is where f prime of x equals 0. That's where we could have local extrema, but not necessarily. It's got to change sign. But where f prime of x is undefined, these are not going to be local extrema. They could be vertical tangent lines in the graph, or they could be discontinuities. In the function or in the derivative. But it's still really important that they're on the number line test, because our function, our derivative behavior is going to change around those areas. So those are critical points. Okay. That's it for our notes today. We're now going to do quizzes.